In our previous work, we have shown how a single agent can learn numerous behaviors in a variety of environments with minimal human intervention. This work looks to take it one step further by allowing the agent to learn without any predetermined knowledge about the inputs it can receive or the outputs it can produce. Instead of hard-coding the hardware that an agent will have available to it, each piece of hardware is able to be dynamically added to the agent. When the hardware is connected, it registers with the agent by providing its name, data type, and a similarity metric to compare data from that piece of hardware. The set of registered sensors, used to sense the environment, and effectors, used to perform actions, can then be used by the agent to observe the expert and perform the learnt behavior. The learning agent will run on the laptop and will not be modified in any way throughout the course of the demonstrations. The agent has no information about the behaviors it will learn, the expert it will learn from, or what hardware it will be connected to. The learning agent is connected to a robot, and each of the sensors and effectors contained in the robot register with the agent. The agent then enters observation mode, while the human controls the robot to perform an object tracking behavior. Using the infrared sensor, the robot is navigated to a charging station until its bumper sensor determines it has come into contact with the charging station. Each input action pair is recorded as a case, and these cases are used by the agent to perform the behavior itself. It uses the current sensory input to search the case space for a similar case and reuses the associated action. The learning agent can then be repurposed to perform a completely new behavior. Again, when the robot is connected, the sensors and effectors register with the learning agent. This registration process not only lets the agent know how it can sense and act on the environment, but gives it the similarity functions necessary to compare its sensory inputs to those stored in cases. The agent then observes the expert perform an obstacle avoidance behavior and creates a new case space. The expert drives the robot forward until it comes in contact with an object and then turns to avoid the object. The learning agent can then use the collected cases to perform this behavior, similar to how it performed the tracking behavior. The agent was able to perform the two previous behaviors without being modified, but it used the same hardware in both demonstrations. We will now show a hardware upgrade where the agent learns with an extra sensor. If the bumper sensor is used to detect obstacles, like in the previous demonstration, the robot could potentially be damaged. Instead, we will add a sonar sensor that can detect obstacles before they are reached. Now, not only do the robot sensors and effectors register with the agent, but so too does the sonar sensor. As we can see, even though the available sensors changed, the agent was able to learn this behavior without being reprogrammed at all. As we have shown, the agent is able to learn a variety of tasks without any knowledge about what it will be learning. Everything it learns is from observing the expert. This allows the agent to be quickly trained or retrained, even if the trainer does not have any computer programming skills. Since the agent is not hard-coded to a specific hardware configuration, it can handle situations where its hardware needs change or it needs to be repurposed for a new task. Each hardware change does not require the agent to be reprogrammed, since the hardware can be dynamically added or removed. The hardware does initially need to be programmed with its information, but that only occurs once. So if a single piece of hardware is used in a variety of situations, then it only needs to be programmed once instead of modifying the agent each time hardware is added or removed.